we're going to do a little bit more weather theory stuff today, okay? This is going to, if you think you've experienced drinking from a fire hose, today you will definitely be drinking from the fire hose. If at any point anybody needs me to stop and be like, yo, what is that? Stop me, please. We will take 1 or 2 breaks depending on what I feel like doing. And if you need more, let me know. If you need to walk out, that's fine too. Keep this interesting for me. Keep me awake. Okay. So this is gonna be miserable for me too. Not gonna have a voice after this. All right. The atmosphere is stable when it resists the movement of air, whether that be upward. Okay. Stable air, if given an upward shove, sinks back to its original level. If it's unstable, it lets it amplify and it lets it continue to move upwards. Okay. Stable air is when the colder air is underneath and the warmer air is on top. Why? Because hot air rises, cold air sinks. So if it's vice versa, that's where that unstable mixing of air is going to happen. Okay? Remember, that's one thing you must remember, is the warm air rises, cold air sinks when they mix unstable. Okay? We all know the lapse rates. How many times have I said it, right? Multiple. Oh, going the wrong way. No. I don't understand the clicker quite yet. Anyways, adiabatic cooling and heating. Have we ever heard that term before? Or if you did the readings. I saw some of you shake your head now. Air cools from expansion as it's lifted and heated by compression as it's forced downward. Remember, we talked about that very briefly, where same kind of concept with that dew point, where like as you can cool the air and make it more saturated, right? Same kind of process. And there's going to be a picture here soon, but occurs without having to take heat away or add it to the particle. It just happens. Okay. Expanding a parcel of air by lifting moves its molecules further apart, keeping them from bumping into each other. The air molecules not being forced to bump into each other creates less friction, and the energy has been used in the expanding particle, which causes the molecules to slow down and temperature to decrease. That's why it gets colder up top. Compressing the air, just like the dew point, is going to, by downward motion, moves the molecules closer together, increasing their speed and increasing the air's temperature. No heat has been added, but it still warms. Here's a picture. So, at the surface, we have an 80-degree parcel of air. As it rises, because hot air rises, right? Hot air, right? We just did that, right? Hot air rises. So as that hot air is rising, that parcel gets bigger and bigger. It's getting stretched out more and more, which then cools it. So what's it going to do when it gets up here and it's colder? Sink. Thank you. Does that make sense? This specific thing, like all this stuff, all of this stuff is not going to be directly asked on the written test. But could you see how this would be useful to know? Obviously, opposite as it's descending air. The environmental lapse rate determines the stability of the atmosphere. If the environment cools at exactly 5.4 degrees per 1,000 feet, the parcel of air will have the same temperature as its surroundings, as if it's physically being moved up and down. The atmosphere will be neutrally stable. The parcel will neither climb nor descend. The air is the same temperature as everything around it. It's going to be nice and calm and still. We went over this sublimation, melting, freezing, evaporation, condensation thing. For latent heat is the quantity of heat energy either released or absorbed by a unit mass of substance when it undergoes a phase transition, a change in state, liquid, solid, gas. Latent heat transactions occur when the water undergoes phase transactions. Ignore that. Words you don't need to know. Saturated parcels of rising air. When the rising parcels cool within a few degrees of their dew point, condensation occurs and the clouds form. Right? Dew point, we're wrapping in last lesson to now. When the cloud forms, heat is released as the water goes from vapor to visible moisture. This latent heat gets released into the atmosphere, and an air parcel condensing into clouds doesn't cool as quickly as one that is not saturated. Saturated parcels of air cool at rates between 2 and 5 degrees per thousand. What's the standard Celsius lapse rate? 2 degrees Celsius. So here's the same picture. It's just showing we have a 70-degree parcel of air. It's moving upward. It got a little bit bigger. Now it's reached its dew point, so there's going to be a cloud, and that cloud gets bigger and bigger as that air rises, trying to catch up to its surrounding temperature. So here's the clouds. You do need to know the different kinds of clouds and the fogs. We'll get the fogs later. The clouds right now, okay? Can anybody name some different kinds of clouds? Cumulonimbus, stratus, any more? Those are the two easy ones. Cirrus, good. There's nimbostratus, there's cirrostratus, there's okay. Cumulus clouds are associated with unstable air. Okay. Stratus clouds are associated with the stable air. So a cumulus cloud, don't worry, you know there's no pictures. The cumulus clouds are those big puffy clouds that you look for shapes in them, and usually we see those in the summer, right? Those big cumulus clouds. Let's see. Those big puffy clouds have a lot of vertical, what we call vertical development. So there's a lot of air going up and down through that cloud. And the thicker that cloud is, like height-wise, say it starts at 2,000, ends at 6,000, there's a lot of action happening in there. It's going to be very turbulent, okay? Those stratus clouds are going to be those nice wispy clouds that kind of streak the sky, right? Not the really high ones, but the ones that are like closer. They just kind of look like a blanket. There's not really a big puff to them. They're just nice and smooth. There's usually very thin. Have you ever had a rainy day where it's still bright out? It's because the clouds aren't thick. It's just a nice sheet of cloud. There's not as much vertical development, which means you're not going to have as much turbulence. So that's why it's associated with stable versus the cumulus are unstable. Those are the two roots that you need to know. Okay, like Latin roots, but cloud roots, right? Stratus and cumulus. Okay. Here's some pictures. So cumulus clouds are associated with the unstable air. Other things that come with unstable air is going to be beautiful visibility. You can see for miles. Okay. If it is raining, it's going to be showery. It's going to like come and go. Like, you know those days where it's like torrential downpour and then it's like a little drizzle and then we get torrential downpour and it all happens in like 30 minutes. That would be showery precipitation. That's going to come with those cumulus clouds, as well as the turbulence we talked about. Okay. The stratus clouds, that beautiful blanket down here, associated with stable air, you're going to have a mucky day. It's like going to be hazy. It's just going to feel damp and wet, but it's going to be actually really good flying weather. It's going to have steady precipitation, just a nice steady rainfall throughout the whole day. Surprisingly, if it looks crappy out, it's probably going to be a nice smooth day to go fly. And if it looks like a beautiful summer day, it's going to be, you're going to be hitting your head on the ceiling. Okay. Obviously not all the time, right? There's going to be beautiful flying days where it is clear skies, couple little puffy cumulus clouds. But rule of thumb, those showery days, as long as those clouds are high enough that that you have space to fly around, it's going to be a nice smooth day. So the difference between the stratus and the cumulus clouds will be on the written. It's going to say what conditions would constitute a stable day. And it's going to give you some different options. Okay. It's going to be like showery precipitation. It's going to, you can use your imagination. You do need to know these four different differences between these clouds. These are the two main types of clouds that we're really going to talk about, okay? Determining the base, there is probably 4 or 5 questions where you need to be able to determine the base of the clouds based on temperature, dew point, and temperature and dew point. And this is how you do it. So, what is the approximate base of the cumulus cloud if the surface temperature at 1,000 feet MSL is 70 degrees and the dew point is 48? This is the math, okay? Have I ever done this math in real life? No. We have weather stations here, right? Now, out west, or you have your own little private airport and you're far away from other airports and stuff like that, by all means, you can do this. You will have to do it for the written. I don't have to do this anymore. So you want to take the temperature and dew point spread. So you want to do 70 minus 48. This is in Fahrenheit, obviously. So if it gives you 1 in Celsius and 1 in Fahrenheit, which it shouldn't do, just remember they have to be Fahrenheit when you're doing this. Divided by 4.4. 4.4 is your magic number. Okay. I don't know how they got 4.4. It's the way that it is. How many times have you heard me say that? It is the way that it is. 4.4. So if you remember 4.4, you can probably create this formula in your head. Okay. Equals 5 times 1,000. So we got the 5 from this equation here. Okay. Times 1,000, because that's the temperature at 1,000 feet. Gives us 5,000, which is going to be the base of those clouds. Okay. Practice. Give yourself some things to do. Just practice when you get home. Okay. Air has weight. We went over this, right? 1 inch by 1 inch of atmosphere all the way up to the top. Weighs 14.4 pounds. This little cube of air all the way up. If we do 1 foot by 1 foot, it's going to weigh 2,117 pounds. You don't need to remember those numbers. Don't waste the brain space on those. Pressure differences, okay? Vacuum cleaners create pressure on the inside, which is how it sucks things into the vacuum, right? Air moves from areas of high pressure outside of the vacuum to areas of low pressure, like inside the vacuum, okay? Remember, it's just the atmosphere trying to stabilize itself. It's never going to do that, but it's trying, okay? There is a constant attempt to equalize any temperature and pressure differences in the atmosphere. The pressure differences are another way in which the atmosphere gets moved, creating wind and weather. Remember, I told you last time that temperature has to do with everything that has to do with weather? I lied. It's also pressure, okay? So while gravity provides a constant pull on the air, the atmosphere still is having variations because it's still trying to neutralize temperature and pressures. Sometimes they are forced upward or downward. Does anyone know which way a high pressure system moves, up or down? Well, I think you know. A high pressure system moves up? So. Yeah. And I'll tell you, I'll show you the rule of thumb here in a second. Rising and descending air. Remember that single cell method, the multi-cell method, or not method, but idea. Can't think of what that word is. That we talked about last time, right? So variations of temperature over the water and land cause those changes in pressure, right? Whenever there's a differential, we have land and sea breezes. There is 1 or 2 questions on the written that has to do with land and sea breezes. Okay. The way to remember which one's the land breeze and which one's the sea breeze is it's labeled with where the air is coming from. So this is an example of a sea breeze. Okay, it's moving from the sea to the land. It's because the ocean is colder, it takes longer to warm up than the warm land. So we have high pressure over here, low pressure over here. So that high pressure is trying to swoop in underneath the low pressure, forcing the low pressure up, and it's a constant circle. That creates some wind up here. Okay. You guessed it, there's a land breeze too. Typically at night, the day's heat keeps the water warm and the land cools quicker at night. So we have a land breeze, high pressure, low pressure, and the breeze is coming from the land back up and around. We're not going to deal with this much out here in Chester County. A little too far away from the ocean to really feel the big effects from this. But it is on your radar. Okay, just a couple questions. Land breeze, sea breeze. You don't need to know why or where the low pressure is. You just need to. It's going to be a question like, which direction does the land breeze come from? Sea, land, or I don't know what the third option would be, but. There's another beautiful picture.
And the high pressure is typically associated with the cooler temperatures.
Yes. And we'll go over that more. Oh, I'm going back. So the land and sea breezes are miniature models of what's happening all over the world. Now our pressure centers. I want everybody to give me a thumbs up with their right hand. I was the only one that had to check which one was right. Come on. I'm kidding. Anyway, so you're giving me a thumbs up with your right hand. How many people are left hand dominant? Do not use your left hand, it won't work. Okay, you have to use your right hand. So right now, not right now, all the time, a low pressure system moves upwards, right? Okay, really get those fingers in there, right? A low pressure system moves up with your thumb, it moves counterclockwise with your fingers, and it moves inward. Okay? See that? Just like the picture. Now, a high pressure, this one doesn't work. As long as you remember the thumbs up one that is low pressure, you're good, just vice versa for the high pressure. A high pressure moves downward, clockwise, and out. Don't curl your fingers in. Does that make sense? I never liked this one. I just remembered this one, and then I could just vice versa switch it around for myself. Please learn that. I promise that if you're a physical, like a visual learner, just giving yourself a thumbs up in the test and being like, yep, low pressure upwards, we're good. I promise this was my instructor taught me this like 5 years ago, and I've always remembered it. Okay. Is anybody confused with that thumbs up thing we just did? Okay. Can you see how it's helpful? So that's just the way that the highs and the low pressure areas move. Okay. You will be asked that on the written. High and low pressure areas are measured by comparison. If the center of an air mass is slightly lower, it makes the surrounding areas higher. Sometimes they span thousands of miles. Within these slowly moving oceans of air, smaller air particles move up and down, as discussed in the stability scenarios. But it's just an area of relatively high or low pressure. Okay. The environment is constantly changing because of these air masses. This is how they would look on a weather map, which you will have to be able to read. All right. There's only a couple questions that you have to look at a chart like this, and there will be a couple variations of what this looks like. But you do need to kind of know what we're talking about here. So we have a high pressure area. Notice which way it's moving. And it's just a kind of a spot. It's not really a spiral, but a bunch of circles, right? Over here, we are lower pressure. You can see in millibars, barometric pressure in millibars, it is 1026. Okay. Over here in the low pressure, it's going to be a lower number, 994. Okay. Yes. Make sense so far? As they converge, they're going to have a little bit, they're going to swoop the other way. The lines that depict this swooping motion are called isobars. Okay. Isobars is important. Okay. There's another word in the aviation dictionary that we're going to learn when we do cross-country planning called isogonic lines. Do not get them confused. There are isobars and isogonic lines, completely different. Not that you know necessarily what those are yet, I'm just letting you know. Remember isobars with this lesson. If they are further apart from each other, think of this like you're reading a terrain chart, right? You see that mountain, if there's a mountain, all the lines are really close together because it's like really steep change, right? And if it's just rolling hills of Pennsylvania, usually they're pretty far apart. Same thing. So over here, these are pretty far apart, right? So the pressure gradient is going to be a little gentler. There's not as much happening. As we get in here, there's much steeper of a gradient, right? So there's going to be more changes, therefore could be more turbulent, right? Tracking? Doesn't sound like you're tracking, but okay. This is what the chart you will have to read is going to look like. You just have to focus on what you're supposed to be focusing on. Don't look at all the colors. You're just looking at these red lines. Does everybody see these red lines? Where they are further apart, there's going to be less of a gradient. And where they're closer together, there's going to be more of a gradient. Really, we choose now. All right. Don't worry, we're almost a fifth of the way done. Here's just another picture of what this stuff looks like. Air doesn't flow straight, it always has a curve. Okay. Really? This is because the Coriolis force that we talked about, right? With those polarlies and westerlies and easterlies and all also caused by the Coriolis effect, our movement of air. Our movement of air has this swoop to it as it goes in or out is because of the Coriolis force. Stuff you don't necessarily need to know, but it is a good background. Does everybody understand why the air doesn't flow straight? Cool. Now surface friction, okay? So although we have these high and low pressures creating wind, we can see up here we have a lot of wind. It's heading in this big red direction, okay? So we get closer to the ground, the wind might change direction and get less because of surface friction, right? Especially if there's a mountain or like a valley, things like that. Obviously, the air in the valley is probably going to flow from the top of the valley to the bottom of the valley, or it's going to flow next to the mountain. There's never going to be air coming directly from the middle of a mountain, right? I mean, think about it, right? So that surface friction, that mountains, all of the terrain is going to affect where that wind is coming from. Has anybody ever flown the Hudson Corridor in New York City? In a small plane? Good. It's a lot of fun. Highly recommend. That should be your treat. After you get your private license. I've done it at night and during the day, two completely different things. But basically you fly below the tops of the skyscrapers through the Hudson Corridor, the Hudson River. You go up and you turn around and you come back down. You fly over the Statue of Liberty, all the big skyscrapers. It's beautiful. You're like right next to these buildings. But I will tell you that one time I did it in a helicopter. We felt every city block. Basically, we were getting battered by wind every block. It was a higher wind day, but those buildings were creating some abnormal wind flows because of technically man-made surface friction. If we were to go above those buildings, the wind would be a different direction. Cool. Surface friction can also be the cause of why they decide to build airports facing certain ways, right? Most of our wind comes from the west, about 290, or that general direction. And so before they build an airport, I mean, I don't know for sure, they probably survey for a couple of years in some area near, at least a big airport. They probably survey to figure out where the wind usually comes from, if they were smart. You don't want to build a runway that always has a crosswind because then nobody's going to be able to land there. Make sense? The surface friction also slows down the wind in most cases. So the wind at altitude is going to get higher and higher because there is less surface friction. There is a couple questions on this, unfortunately, things that you probably will not use in your flight training, but you still need to know. Pilots on long cross-country flights can take advantage of these high altitude wind flows and gain tailwinds and avoid headwinds. Why would we want to do that? So our trip goes faster. On east to west flights, from west to east flights, so if we were to go from California to New York, we would want to fly north of a high pressure system and south of a low pressure system, just because of where the air is, the direction of air moving. So that's why sometimes you see airliners do big S's, or not big ones, but they might change their course a little bit. They're trying to take advantage of those high altitude winds. Cool. And then vice versa. On east to west flights, you want to fly south of the high and south of the high and north. Anyway, south of the high and north of the low. Does that make sense though? There's like one, maybe two questions on this specific topic. Just remember this picture. Wind correction angles in highs and lows. This is what your wind correction angle would look like. Not that you're ever consciously like, okay, I'm flying over a high pressure system, I must wind correct a little bit this direction. You never think that way, okay? I promise you. Nor will there be questions on it. Determining the location, if you really wanted to, determine the location of a low pressure area. I've never done this. You could stand with your back to the wind, rotate 30 degrees to the right to compensate for the effects of ground friction. Your left hand will point in the direction of the low pressure system. Fun fact. I've never done it, never have to do this, but if you were curious, you can. Isobar spacing and wind speeds. So we kind of already touched on this. Isobars are spaced closer around low than high pressure, typically. Isobars are spaced at a pressure of 4 millibar differences. You do need to remember, there is a 4 millibar difference between each of those ones. The closer they are together, the more rapid the pressure change. We got that. Rapid pressure changes mean faster winds. So we're gonna have a lot more wind over here than we are gonna have right here. Okay. In addition to wind direction and speed, high and low pressure centers have their own weather associated with them. This is something you will need to know. High pressure centers are colder and denser air masses, which is why they move down, because cold air sinks. Okay. High pressure, opposite. Warmer air, and it's going to rise. Really? We got through like 50 slides with no problem. It spreads out. It spreads out in all directions from the center of the highs, and obviously scoops in if it's a low pressure system. Coriolis force causes it to curve a little bit to the right in a clockwise circulation. It's going to be the opposite for the low pressure. As high pressure air descends, it warms due to compression, decreasing the relative humidity. Are you? Clouds are less likely to form, and clouds that are present are likely to dissipate. So the high pressure, cold, downward moving air probably won't be cloudy. Low pressure centers are warmer, less dense, they rise. It's all going to be the exact opposite of what we just talked about, right? Convergence in the low accelerates the air and wind speeds increase. Wind velocities are higher around a low than a high. Lows have rising air that expands and cools. If the air within the low approaches its dew point, condensation occurs, clouds appear, and weather gets worse. The only practical time that you can really use this is when you call a weather briefer, because you'll do that during flight training. And they're like, yeah, it looks like there's a low pressure system moving in. Well, as a student pilot who did not know what a low pressure system was, that meant nothing to me. It means something to me now. And when they say, oh, looks like you're in a high pressure area, I'm like, dang it, that means it's not nice. Does that make sense? So it is useful, but it doesn't tell you what the clouds are going to be at, what kind of precipitation, what wind speeds. It doesn't tell you all that. It just says you're going to have good weather, you're going to have relatively bad weather. Okay? High pressure systems are cold, sinking air. Low pressure systems are warm, rising. See, it's not second nature for me. Divergence is high. You will not have to know the word divergence and convergence. I don't think that's on the written test at all. You just need to know the difference between highs and lows. Now we get troughs and ridges in here. All right, these are easy, I promise. And you do have to know those. A trough, think like an animal trough, it's a bucket, it's really low on the ground. And a ridge, like a mountain ridge, is going to be up high. So a ridge is an elongated area of relatively high pressure, and a trough is going to be an elongated area of relatively low pressure. Troughs and ridges. So we have isobars, troughs, ridges, I think are big two new vocabularies today. Here's a better picture of what a trough versus a ridge is going to be. I don't really need to know much more about that. This is all regional stuff. Not on the written, just good background knowledge. If you would like to go through this, by all means, you can go through that. Highs and lows are associated more than just horizontal flow of air. They attract and repel massive moving wedges of air known as the frontal systems. Air masses of different densities that bump into each other cause confrontation. The differences in temperature result in the difference in density, which don't mix readily. So those systems are they're bumping heads. It's called a front. Okay, have we all heard of different fronts, right? Oh, we have a warm front coming in, or anyway, cold air. This is where this little swoop is where these fronts usually go. But the cold air and the warmer air bump into each other. That's what makes everybody have unique weather patterns. Background information. Front within a trough, pressure falls at the front, it approaches because the fronts are often found along low pressure troughs. Cold fronts lie along the border between two high pressure areas. As the front approaches, the pressure falls. It increases after a frontal passage since the high pressure area lies behind the front. Convergence in a trough. So we have warm, moist air and cold, heavier air. And so it's going to push up. Look what that looks like. Lots of lifting action, lots of thick clouds, and we have a little storm forming. That's just how something would form. A front is a boundary or a transition zone separating the air masses having different properties. As you cross the front, the properties change. Temperature is the most easily recognized difference in the fronts. Have you ever had a nice warm summer day and you just felt the rush of cold air right before it's about to storm? You're feeling the front. Pilots flying across the fronts are going to notice that temperature change. Since relative humidity varies with moisture content of the air, as well as temperature of the air, expect changes in dew point with that frontal passage. Wind shifts across the front because pressure changes, right? Don't have to know this for the written. Nor are you flying this far across country to really feel that as a student pilot. All right, cold fronts. Cold air mass overtaking a warm air mass is a cold front. Write that one down. That one's going to be important. Cold front is cold air overtaking warm air. Cold air is heavier than the warm air. It moves along the surface. It pushes that warm air up like a snowplow. This is what it looks like. The leading edge of the cold air sticks to the surface because of its weight and surface friction. It forms a steep sloped frontal edge. See how it's steeper right here and then it gradually smoothens out. So that warm air is just going to go right on top of it. Faster moving cold fronts have steeper frontal slopes than the slower ones. The frontal slope ranges from, it doesn't matter. All you need to know is that a cold front is when cold air overtakes warm air. Got it? There are two types of cold fronts. Cold fronts can be divided into two categories, fast and slow moving. Very creative with the naming, at least you guys don't have more words to remember. Fast moving cold fronts have been clocked in excess of 60 miles per hour. On average, they move around 30. Their speed is generally faster in the winter than in the summer. Think the cold air likes the cold weather, so it moves faster. I don't know how you want to remember that, but that's how I would remember it. Most of the cold front cloudiness and precipitation is located ahead of the area where the warm and the cold air meet. Because the cold front's high speed, this weather is often the most hazardous that pilots encounter. We have a whole bunch of different kinds of clouds. All right, right here we have cumulonimbus. Right here we just have a cumulus cloud. Got some altostratus in here. You don't know any of those, that means nothing to you. That's okay. We're gonna learn it. Squall lines can also come from this kind of thing. Fast-moving cold fronts can generate squall lines 30 to 180 miles in advance of the parallel front. I saw one of these the night of my engine failure. I didn't know what it was at first. Had nothing to do with the engine failure. It was just one more happy memory for that night. Squall lines are lines of thunderstorms. You can see a long line of thunderstorms building. They can be dangerous because you can't really go around them. You don't want to go over and you don't want to go under them or anywhere near them. Does anybody know how far away you're from a thunderstorm you're supposed to start? 20. Yeah, that's funny. I don't fly if there's a thunderstorm. Like, if the thunderstorm is like at Lancaster, I'm not going to take off. It's at Reading, because usually they come from like the west or the north kind of areas. If they're at Reading or Lancaster, I'm not going to fly at all. If they are, I might do a couple laps in the pattern, depending on what I have to go. Cool. There's a pressure wave. You just need to know the squall lines are bad. Elongated areas of thunderstorms. Slow moving cold fronts usually generate less hazardous weather. They form shallower slopes. See how shallow and nice it is for that warm air to just bump right over it. So we're gonna get some stratiform clouds. Sometimes, if the air is already unstable, you can get some cumuliform clouds, but typically nothing crazy. Okay. No big thunderstorms. Oh, wait, go back. We didn't do this. I know where this is going now. I see you moving, Dennis. Warm fronts in stable air. They follow the small wave pattern moving along the polar front. Retreating cold air in the upper part of the wave is replaced by the warm, moist air from the south. Has anybody ever seen this on the Weather Channel? Yep. Being heavier and denser, the retreating cold air is tugged by the surface friction more as it moves. So they're going to kind of go slow. Tugging creates a shallow slope, which the warm air mass gradually rises gradually as it replaces that colder air. Cold air is reluctant to give way to lighter air. Okay. They usually move at 15. So we started at 60 for the really fast moving cold fronts. Now we're like half of that is the slower moving cold fronts. Half of that is going to be around the speed of these warm fronts. I don't care what the slopes are. If the rising warm air is moist and stable, stratiform clouds will develop in the warm front, those nice happy clouds. Sequence of cloud formation encountered in advance of the warm front is cirrus, cirrostratus, altostratus, and nimbostratus. Precipitation increases gradually within the approach of the warm front and continues until it passes. Embedded thunderstorms are likely in the stratus cloud mass if the air is being lifted by the warm front and it's unstable. We need a couple things for a thunderstorm we'll talk about in a bit. Lifting action, moisture, and what? Precipitation. I hear you. Widespread precipitation ahead of the warm front often causes low stratus and fog. You're not really going to be quizzed on what's these things associated with these warm and cold fronts. One's good, one's bad, generally. The precipitation raises the humidity of the cold air to saturation. This produces those low ceilings and poor visibilities over a wide area. Does everybody get the gist of a cold and a warm front? It's okay if you don't. There's stationary fronts too, okay? Sometimes the opposing forces exerted by the air mass of different densities are similar and no movement occurs. This is what they look like on a weather chart. A little mix of cold and warm. With little to no movement, they're stationary. Wind on either side of the boundary blows parallel to it rather than across it. So the wind is going sideways instead of trying to push each other. While stationary fronts are stationary, they do move a little bit, 5 knots. Weather that forms is similar to a warm front, but less intense because while there's little air exchange, there's not a whole lot of movement. And these usually last for several days. Wave cyclone weather patterns. Okay. Before this class, I've never heard of them. Not on the written. Not on training, nothing. A cold front occlusion. There's 4 types of fronts. It's cold, an occluded, a warm, and a stationary. The acronym is COWS. Okay, you need to remember that that's a front. It is, right? It's in the book. Cold fronts will catch up and overtake a slower moving warm front. This overtaking is that cold front occlusion. Okay. Cold occlusions occur when the air ahead of the warm front is less cold than the air behind it and the overtaking cold front. The cold front overtaking the warm front lifts the warm air up and over the retreating cold air. So remember, a cold front is when the cold air mass overtakes, pushes the warm air out of the way, right? This one is, there is already a warm moving front. The cold air comes up behind it and kind of covers it. That's the difference between these two. The warm front is lifted entirely off the surface by the undercutting cold front. Oop, it's gone. Weather ahead of the occlusion is similar to that of warm fronts. The weather near the surface is similar to cold front. Well, ahead is similar to warm fronts. The weather at the surface position is similar to the colder fronts. As the occlusion develops, warm air is lifted higher and higher. Finally, the clouds associated with it disappear. The weather and the cloud systems now resemble a cold front. This is the one gets talked about the least. Usually the big ones are your cold and your warm fronts. Stationary and occluded are not asked about on the written. You might have to point out what they look like on a weather chart, but you will not have to know describe, have this described. And seeing if it had a picture, stand by. No, it does not. Sometimes I think they're purple on the chart. There might not even be a question with these occluded fronts on the written. Warm occlusions are found in the Northwest United States, so not around here. Occurs when that Pacific cold front pushes the warmer air up over the retreating Arctic air mass. Pacific air, this is not on there. I've never been quizzed on warm occlusions, but the weather is similar to a warm front on the east, and the cold front weather occurs near the upper cold front boundary. My best advice would be to watch a YouTube video, because that's what I did. Because when my teacher tried to explain this to me, they could have explained it a million times and I would not have understood all of this. All right, take a 5 to 10 minute break. If you need to sign your name on the it's over here. You need to sign your name on the attendance sheet. Please sign it. If you want your if you were not here in the beginning and did not get your midterms back, please come up here. Does a high pressure system move up or down? What?
Down.
Down. Right?
Yeah.
Wrong remote. Okay. This is important. This we do pay attention to. Cloud is a visible aggregate of water drops. I don't know what it is. You can see if there's moisture in the air, right? Because that's what a cloud is. Yeah. Fog differs from a cloud only because the base of the fog is at the surface, while the clouds are above the surface. They're the same thing. Okay. Clouds provide information on air movement, stability, moisture, which help us visualize what's happening, right? You can sit here and you can watch how fast that cloud is oddly moving over your airport, and you're like, my direction of flight is that way. It's going to take me a long time if the clouds are moving that fast. Once again, also, if there's a lot of vertical development, if they're really thick, there's a lot of up and down movement, it's probably going to be bumpy. If there's puffy clouds, it's probably going to be bumpy anyway. And if they're the nice flat clouds, it's probably going to be a little smoother. For clouds to form, you need vertically deep cloud. Rising currents of air are necessary for the formation of vertically deep clouds, which would then be capable of producing rain. There are 4 kinds. Okay, write this down: cirriform, nimbus, cumuliform, and stratiform. Okay. Does anybody know what nimbus means? Rain. Yes, but thunderstorm as well. I'm just sitting down for a minute. My knee's starting to hurt, so I apologize in advance. So, cirriform clouds. High-level clouds above 20,000 feet, usually composed of ice crystals. You're not going to be quizzed too much on these because you don't really deal with these as low-altitude pilots. High-level clouds are typically thin, white in appearance, and can create an array of colors. Cirrus generally occur in fair weather and point in the direction of air movement at their elevation. They're those flowy ones up in altitude. Nimbus. Nimbus means rain. Typically form between 7 and 15,000 feet and bring steady precipitation. You don't need to know what altitude, just need to know that nimbus means rain. As the clouds thicken, the precipitation begins to fall. The bases of the clouds tend to lower towards the ground. Cumuliform. Clouds look white and fluffy, or heaps, and show the vertical movement or the thermal uplift of the air in the atmosphere. The level at which condensation and cloud formation begin is indicated by the flat cloud base. They're going to be like your stereotypical drawing of a cloud where it's flat and then puffy. Okay. The more humid the air, the lower the cloud base, because dew point. These clouds can get up to 60,000 feet, right? They can be big boys, especially if it's associated with a thunderstorm. Stratiform. Stratus is Latin for layer or blanket. They consist of featureless, low layers that cover the entire sky like a blanket, usually bringing gray and dull weather. Typically, they're only a few hundred feet above the ground. And over hills, they can, like, have you ever seen the mountains sticking on top? Technically, right there would be fog, right? It's at that ground level. I've never actually, I have seen it. Very, very little bit of mountain coming above the cloud. As fog lifts off the ground, due to daytime heating, the fog forms a layer of low stratus clouds. So here's a picture of all of them together. Okay, then we also got some altostratus, altocumulus, but we're just focused on the four main ones. Okay. High cloud, you don't need to know this, but high clouds are over 20,000 feet. Middle clouds are 6.5 to 20,000, and low clouds are surface to 6.5. High clouds in general are typically white and thin. They can have all those colors. Okay. Cirrus, cirrocumulus, cirrostratus. Oh, notice all of the cirrus clouds. Okay, so cirrus, CI. Cirrocumulus, you don't need to know the different, this is just pictures of what they look like. Cirrostratus. Middle clouds, altocumulus, altostratus, altocumulus standing lenticular clouds. We'll get to that one. That one's my favorite. Nimbostratus, composed of water droplets. However, they can be composed of supercooled liquid water droplets and or ice crystals when temperatures below are freezing. So here's what altocumulus looks like. Pilots flying through your altocumulus can expect some turbulence and small amounts of icing. Altostratus, pilots can expect no turbulence, little to no turbulence, but light and moderate icing in the supercooled water regions. I don't know why. So there's this thing when you're learning something where it's like the idea of primacy, where the first thing that you get told you're gonna like remember like the best, right? And then it's like a hard habit to break or a hard topic to break. And when my teacher first was telling us about these lentil clouds, I saw lentil, not lenticular. So I just think lentil clouds now. And they look kind of in their pictures, the animated pictures, they literally look like a little lentil in my head. And so that's how I remembered. No, now you guys are all cursed with that. These formations are caused by wave motions in the atmosphere and are frequently seen in mountainous or hilly areas. The clouds as a whole are stationary or slow moving, and you can expect severe turbulence. They are packed with turbulence. If you see a lentil in the sky, don't fly near it, because especially in our airplanes, severe turbulence is not something you mess around with. Even severe turbulence is something airliners try to avoid. All right, so if you see a little nice, thin, pretty, beautiful cloud that's not moving, don't go near it. Okay. Nimbostratus, officially classified as a middle cloud, although it may merge into very low stratus or stratocumulus clouds, and could be a low-level cloud. They can pose serious icing problems if temperatures are near or below freezing. Now these are the ones we care about. All right, cumulus, towering cumulus. Can we kind of put that together? Yep. Stratocumulus, stratus, and cumulonimbus. Okay. We all know what that one is. That's like the most common thunderstorm. General population knowledge, cumulonimbus cloud, right? They are composed of water, however, they can have ice in them. Cumulus, those puffy clouds we talked about. Towering cumulus, you guessed it, it's cumulus cloud, but it's towering. Stratocumulus, highest liquid water contents are in the tops of the clouds where the icing threat is the greatest. You won't be quizzed on this one. I think I've really ever dealt with a stratocumulus cloud on my written test. The main ones are your stratus, your cumulus, and your cumulonimbus clouds. Okay. Stratus produce little to no turbulence, but the temperatures are near below freezing, can create icing. Have you noticed if the temperatures are near below freezing in the clouds, you might get icing because it's water. As it hits your metal or fabric wing, it's going to turn into water on the wing, and it's going to freeze. It's going to turn into ice. And guess what? We have icing, which we'll talk about here in a second. Stratus fractus and or cumulus fractus clouds. Ragged shreds of low clouds appear and associated with other clouds. Fractures of clouds. You won't be quizzed on that. Cumulonimbus are especially dense and vertically developed, occurring either as isolated clouds or a line or wall of clouds. Composed of water and ice. And they contain snow, water droplets, things like that. Cumulonimbus clouds contain nearly the entire spectrum of flying hazards, including extreme turbulence, icing, torrential downpour. Stay away from those, okay? And you can't really tell the difference between a cumulonimbus cloud and a regular towering cumulus cloud. So that's why you have to be careful. Here we go. There's another beautiful picture. Does everybody see this little thing here? How it like is the cloud, but it like protrudes out again. That is called an anvil cloud, right? It's an anvil. Do we see how that resembles an anvil? We have to be careful with those because there is some questions about flying around an anvil cloud. If you go under it, I just tried to push to show that my pointer is going under the cloud. If you go under it, you can also experience severe turbulence and the effects as if you were flying next to it. So don't try to fly under the anvil of the clouds because you could still be in danger. Cool. Thunderstorms. Thunderstorm is a local storm produced by a cumulonimbus cloud, always accompanied with lightning and thunder, usually the strong gusts of wind, heavy rain, and sometimes hail. The total life cycle is 20 to 90 minutes for one thunderstorm. Thunderstorms are barriers to air traffic because they are usually too tall to fly over, too dangerous to fly under, and can be difficult to circumnavigate, go around. There are some ingredients. You need water vapor. Virtually all showers and thunderstorms are classified as unstable. So you have to have unstable air. And you need a lifting mechanism. So we have water vapor, unstable air, and lift. Write that down. We'll take a picture. That will be on the test. And they ask it in 3 different ways. They ask it a couple different ways. I don't know if it's exactly 3. They're going to be like, what are the 3 ingredients for a thunderstorm? Under what 3 factors are necessary to create a thunderstorm? They love to be wordy. There's like a bunch of questions on it. So converging winds around lows and troughs could be your lifting mechanism. Fronts, upslope low, as in like a mountain and the air is being pushed up the mountain, could cause your lifting action. Local winds, like those sea breezes and land breezes. And there's 3 stages, okay? So there's 3 things you need, and then there's 3 stages. These are important as well. You also need to know the order. Cumulus stage, mature stage, and dissipating stage. So the cumulus stage is the first. They're given their initial shove, air particles. The cumulus cloud grows and becomes moist. Sorry if you don't like that word, I know some people are weird. Latent heat is released and the moisture condenses, making the cloud warmer and accelerates its growth. As the more moisture latent air is drawn into the cloud, the condensation process continues, producing additional cloud droplets in the updrafts. The only thing keeping the raindrops aloft is the updraft. So as soon as that updraft stops, it's all going to rain down. Oh. You can get an excess of 3,000 foot per minute updrafts. Can you imagine what that's going to feel like if you fly through it? You're going to hit your head on the ceiling. Mature stage, characterized by downdrafts, updrafts, downdrafts, turbulence, low-level wind shear, hail, ice, rain, and lightning. This is where you see the thunderstorm happening. Most dangerous. Eventually, the water droplets fall. First sign of rain on the Earth's surface begins that stage. Rain descends through the cloud. Hail is most likely to occur. Has anybody been in an airplane and seen the rain under a cloud? It's absolutely beautiful. In my pilot training, I was not always responsible certified flight instructor Kenzie over here. And I remember taking my friend's plane with him. We were so smart that day. We flew formation over the ocean at the beach, playing around, like diving under each other legally. Okay. And then we were coming back and I wanted to fly over my house to like say, I always draw something over my parents' house because they have flight radar. And we were gonna go fly over my parents' house. And there was one of these like right over Oxford. So we were like, we can almost see through. We're just gonna scoop the outsides. His windshield has a little bit of a leak. We found out we got soaked in rain and quickly turned around. I don't think it was like a thunderstorm. I think it was just like one of those like very heavy summer showers where like it's muggy all day and it just deluges and then it's good for the rest of the day. Don't fly in it. If that wasn't even a thunderstorm and I already dealt with that, don't fly in a thunderstorm. Don't be stupid. And then I was all covered in water. And his dad got mad because we found something wrong with his plane. So don't do it. And then the dissipating stage. The updrafts weaken. The downdrafts are what's left in the thunderstorm cell. It rains itself out. And the dissipating stage is often characterized with that anvil top, because that wind direction is kind of getting pushed away. This is another picture. Got a lot of lifting. It's all coming back down. This is just how different thunderstorms form. You will never be quizzed on this. They are all the same. Squall lines is the same thing, associated with tornadoes as well. Okay. Develop 30 to 180 miles parallel to a fast moving cold front. Talked about that. Squall lines can seen, as seen here. You all see how there's a big giant line of thunderstorm. You see how if you're an airplane right here, you'd have trouble getting around that. Land. Here's another picture of the movement. Turbulence. Thunderstorms have the capability to give a lot of turbulence. We talked about that. And the first gusts, one of the significant hazards produced by thunderstorms. During the mature stage, rain begins to fall underneath the cell. A massive gust of cold air shoots down to ground level and spreads out in a horizontal motion, like the picture. Winds from 20 to 100 knots and higher within 150 feet of the ground have been reported. And you see how this is going to be very hazardous. It might not even be raining quite yet. It's the first little swoop. Can be within 10 to 15 miles, most intense 10 to 15 miles from the storm. Effects have been seen 50 miles. There is a name for it. I'm trying to see if it's going to tell you. No, it's not. Cool. Thunderstorm avoidance, 20 miles. Okay. Never try to do this. It's not worth it. You don't know what if they're moving together for whatever reason. You don't want to get stuck between them. That is how pilots die, right? Everything's written in blood. Cockpit weather. So we have weather in our airplane. That's great, right? Who thinks that's great? Then we can see the clouds. Oh, we got one. He's brave. You're brave. You're brave. Never, ever, ever trust that weather that your airplane gives you. It can be 10 to 15, even 30 minutes delayed. And so you could see that red splotch and you're like, yeah, I'm clear of it. You're not clear of it, especially embedded thunderstorms where that weather, because that weather is just coming from a ground station up to your airplane. So it's not coming, our little airplanes don't got a little radar in our nose that's bouncing back where these storms are. Okay, it has to get it from ground or satellite back to your airplane, and that takes a couple minutes. And those couple minutes can, if that thunderstorm's traveling fast enough, you think you're 20 miles away, and now you're not 20 miles away anymore. And there's no way to outrun it, right? Unless you react quick enough. So he's seeing 30 miles away, he's got this big purple thing. I don't know if these are the same picture. But you can, if you're in the clouds and there's embedded thunderstorms, you can get yourself into some trouble because you can't see that towering cumulus or cumulonimbus cloud. You're just trusting your weather that is late. Okay, so never trust it. I do have pictures of the airplane that I was not flying. It was a Cherokee 6 actually. I was in the back seat and we went through a couple thunderstorms one night. It was nighttime, it was even worse. And we got 2,000 feet per minute downdrafts trying to climb out of Charlottesville in Virginia, I think that is. Mm-hmm. And I have like a picture and we're just in the giant red squall line and red and purple. I was like, glad to get back home that night. Don't do it. It's not worth it. There's nothing that you need to go do that you can't go Uber to or wait a day. Make sense? This is what your weather can look like. We'll talk more about it, but that 10 to 15 minute delay is like the most important. Okay. Oh, I'm going backwards. All right. Virga. Variable intensity rain gradient aloft, called virgin rain because the rain doesn't touch the ground, occurs when the rain falls and evaporates before hitting the surface. I've never seen it. You won't be quizzed on it, but it is a thing that happens. It does rain sometimes and it doesn't hit the ground. Sometimes associated with severe downdraft phenomenon known as microbursts. Okay. Microbursts produce downdrafts containing wind up to 150 knots that typically last 2 to 5 minutes. That's great, right? It's only 2 to 5 minutes. There's been a lot of airplane crashes because of microbursts. Okay. An airplane attempting to, is there a better picture? Here we go. So this is a microburst, okay? So, we got that strong downdraft, and then it hits the surface and bounces outward. So this is fine when you're not near the ground, right? We don't care that much. You're gonna lose some altitude, it's gonna suck, it's gonna be bumpy. But if you're near the ground, it's going to push you, if you're, if this was only a little bit further, that's gonna push him back into the ground. As he takes off, you can see he's losing his air, and it's pushing him down, and then it's throwing him forward. Same thing if you're on final trying to land. Suddenly you have this headwind, you're like, oh, look at that headwind, and then you're shot down, and then you have this horrible tailwind that launches you forward. It's only 2 to 5 minutes, but when they're near an airport, they are the most dangerous. Most airports have microburst warning systems to kind of help people out, but this will roll especially our airplane, you're toast if you get into one of these in our airplanes. So we try to avoid flying. If you sense a massive headwind hit you, you're probably here, right? And that's your sign to abort whatever you're doing. Fine. And turn around if you can. Cool? Not to scare you already. Turbulence and wind shear. Wind shear occurs. Wind shear is just a rapid change in speed or direction of wind. We have it all the time here in the spring and the fall, and the summer and the winter. Okay. We always have wind shear. It's been killing us lately. Today it was crazy. I was sitting outside watching the windsock, and the wind changed 180 degrees while an airplane was landing. He had to go around. And it wasn't light wind. It was like the windsock was completely out. And he went around, and his takeoff was kind of scary to watch. But wind shear is dangerous, the direct change in direction, but also the change in speed. If it's a nice subtle 10 knots of wind, you're coming into land, and then all of a sudden it's 30 knots, and you're like, holy crap, and then it disappears, and now you're low on airspeed, you're low on altitude, and you should go around. So that's why we watch out for wind shear. Can be caused by terrain, buildings, trees. You suspect wind shear, go around. Convective turbulence, quite noticeable at low altitudes during approach and landing. Uneven heating of land along causes variable concentrations of heated air near the surface. Not on the test. Background information. Somebody's walking around the hangar. Stand by. It's just a line guy we're doing. Smooth air above cumulus clouds. Turbulence occurs beneath the clouds. It should be smooth above. Doesn't mean you can always get above the clouds, right? Doesn't mean it's always smart to be above the clouds. Why wouldn't we want to be above clouds? Because when your engine dies, you can't see all your options of places to go, right? You don't want to get stuck on top of a layer and not be able to get down. Mountains cause these lenticular clouds with a lot of turbulence. See how they kind of look like little lentils? See that? Won't be quizzed on that. Here's more lentil clouds. That's what they look like, severe turbulence. We also have rotor clouds, which I've never heard of before. We don't train around mountains, and it's not on your test. There's more lentil clouds. Pilots, you must be cautious when around the mountain wave clouds. They can form in dry air, which are not visible. Winds can exceed 25 knots at the mountaintops. Don't fly right over a mountain. I've also maybe done that a couple times. It's not smart. You should give yourself some altitude as a buffer. Fog. All right, get your pens out. I hate fog. Right? You're gonna hate it too. You have to know the differences in the fogs. How many different fogs do you think there are? Somebody who didn't read the slides. 2? I see a couple people holding up 2. There's like 5 or 7. It's miserable. Fog is a cloud that touches the ground. One of the most frequently causes surface visibility issues. Once again, who has flown in the summer here? Who has flown at 8 a.m. in the summer? Probably didn't, because there's always fog on our runway in the summer. Prevents a serious problem, but is because they form in a very short time, but usually they dissipate in a short time as well. No. All right. No, not what I thought. The dew point and the temperature are the same. Fog. First one, radiation fog. Okay. Okay, the ground radiates its heat away. Okay, that's the way you're going to remember. On clear, calm nights, so terrestrial, I got it. Terrestrial radiation of the heat cools the ground. Okay, the sun's not there to keep the ground warm, right? This allows the air resting next to the surface to cool quickly. As the air cools to its dew point, the water vapor condenses, makes fog. Radiation fog is common at night and early morning hours. So that fog, when you wake up and you're like, oh my God, I can't see anything. Didn't we have like a really bad fog spell last summer? Or like you could, maybe it was just around here, but it was horrible. Like you couldn't even, like some people didn't even drive. I was one of them. It was like I'm not a wuss when it comes to like driving and restricted visibility. You could not see in front of you. But anyway, that's going to be a radiation fog. Areas of high humidity, bodies of water aren't a likely place for radiation fog to form because they don't cool as quickly at night. Winds up to about 5 knots tends to mix and deepen the layer of fog. Higher winds disperse it. So if the winds pick up higher than 5 knots, it's going to be gone. Solar heating of the earth after sunrise also dissipates this fog. The reason we need to know, why do we have to know all the different kinds of fog? You should know all the different kinds of fog because you want to know when it's going to form and how it's going to disappear, right? So if we know what kind of fog we have, we'll know how it's going to disappear. Will I fly when that sun rises? Yeah, probably. If it's a different kind of fog, it might not. So radiation fog, ground gets cold, dew point lowers, fog forms, not a lot of wind, more wind, it disappears, sunrise, it disappears. Got it? Radiation fog. Advection fog. These are going to be your 2 main fogs, okay? Convection means to move something vertically. Advection means move it sideways. As warm, moist air comes in contact with the ocean's surface, the air temperatures decrease and water vapor condenses. Questions on the test are going to be like, where is advection fog going to form? So the key word in one of those answers should be ocean, right? Because this only forms around the ocean, okay? With slight heating, the pressure over the land lowers, drawing the advection fog inwards, right? Remember that sea breeze that pulls it in? Advection fog deepens when the winds increase about 15 knots. And winds above this speed tend to lift this fog into low stratus clouds. Okay. So this one, a little bit of wind isn't going to dissipate it. Okay. Advection fog can form quite rapidly and extend over large areas. So, advection fog, ocean, low pressure, pulls it inland. Now it's over the land. Hopefully it disappears when the dew point temperature separates, okay? but it's gonna be pulled over the wind. Precipitation induced fog. It's been steamy outside when it rains, right? That's probably your precipitation induced fog. Warm rain falling through the cold air and bring fog, basically. Associated with warm fronts and can occur in slow moving cold fronts and stationary fronts. Notice there's not as much on this one. So precipitation induced fog, your key term, it comes with the rain. Okay. Upslope fog, also easy to remember. When the warm, moist air is forced up a slope, it condenses and creates fog. Have you ever seen the mountains, the like little misty stuff around the mountains? That's just upslope fog. That warm air was forced up, now it's colder, and it made fog. Steam fog forms over bodies of water. Okay, steam, water. Dry, cold air passes over a warm body of water. The moisture evaporates rapidly from the surface. Condensation takes place and the cold air is quickly saturated. Cool. So steam, think water, steam. Okay. Not to be confused with advection fog. Ice fog. Guess what? It's basically the same thing as radiation fog, except it's freezing outside. Okay. Water sublimates directly into the air as ice crystals, temperatures around -25 degrees Fahrenheit. We don't get that around here too often, so we don't have to worry about this one. Those are your kinds of fog. How many was that?
6.
6.
You say the ice fog one more time.
It's basically advection fog, radiation fog.
Okay.
Okay, but it's freezing temperatures, so it forms the same way. Questions on fog? Wasn't that bad, but you have to memorize. So my advice is just memorize all the different kinds, make an acronym for yourself. I don't know an acronym off the top of my head, but just know all 6 of them and be able to just define each of them. Some of them are self-explanatory, right? Frost. Okay. Frost forms same way as dew. Difference is the dew point surrounding the area is colder than freezing. Right? We all know what frost is. The temperature of the collecting surface is at or below the dew point of the adjacent air. Why is frost dangerous? It disrupts the airflow over the wing. So, if we look here, our clean wing has a nice, pretty airflow, right? If we have frost, it's going to contaminate that little surface there. It's going to contaminate the whole surface, especially if your, say, airplane was left out overnight, right? And it's going to cause you to stall sooner at a lower angle of attack, okay? So you could take off, as soon as you rotate, stall, and crash, and not be able to recover. Just because you had a little bit of frost on your wings. Now, obviously, is that going to happen every time? No. So if you do it once and you get away with it, now you're going to get too cocky and you're going to do it again, and the next time you're going to have issues. Don't fly with frost on your wings. Take a rag and wipe it off. The whole airplane, not just the wing, the top of the airplane. And you don't get that when you're here at Chester because we keep those morning flights, if it is cold, in the hangar so that they don't get frost or cold. Make sense? Just be careful with where that airplane was stored, especially in the winter. Okay? Frost, bad, kind of icing. Okay? Speaking of icing, except for the freezing rain, it's unlikely you'll experience icing in VFR flights. Okay? What 2 things do you need for icing on your airplane to occur? Does anybody know? Visible moisture and near freezing temperatures. Okay? Emphasis on near freezing temperatures. You know, metal gets colder like faster, right? So it might be like 2 degrees Celsius outside, but your wing's still like -1, right? For structural ice to form, you must have visible moisture and near freezing temperatures. One exception to structural icing is freezing rain. Okay. Once again, it might not be cold enough outside for that rain to be, for that rain to be snow, but if the surface of your airplane is cold enough, as that rain contacts it, it's going to turn into ice. Stop yelling. This can result in the greatest accumulation of structural ice any pilot might experience. So you have to be very careful. No near freezing temperatures and moisture. It's okay if you fly in the freezing weather. Then it's okay, as long as you're nowhere near cloud, nowhere near fog, anything like that. Okay? If you encounter icing conditions, whether that be freezing rain or snow, make an immediate 180-degree turn, because a minute ago you weren't in those conditions. We want to go back where we were. Okay. Ice accumulation. Ice accumulates unevenly, and it increases weight and drag, and it's uneven. Landing approaches should be made with minimum flaps and added speed, if you do have to land with ice. Once you get it, I mean, you can't really get rid of it, right? You messed up. Avoid sudden changes in anything. One more thing with ice, there are different anti-ice things that you can, I'll get to you in a second. There are different anti-ice technologies. There's boots, there's feety, like fluid, and there's heaters. We don't have those in our airplane. The Cirrus do. But in the regular trainers, we don't have that. And once you have the ice, it is an emergency, you need to land. Go ahead.
Sorry, do you not use the flaps because the added weight and also you have a chance of being unbalanced now that you have the ice forming on the way?
You don't want to put flaps in because the ice is creating drag and the flaps also create drag.
Okay.
So you want to minimize the use of the drag. Have I had ice before? Yeah. I was not always responsible flight instructor Kenzie, but I learned and I'm here. And my classmates have definitely gotten it. They were up at Reading one time. They emergencyed into Reading because they got ice on their little Skyhawk, and tower let them get out as soon as they were clear of the runway, and they wiped the ice off the leading edge. They took a video of this giant ice chunk just falling on the ground. That was years and years ago, but don't recommend. They got in trouble for having that video because they should not have put themselves in that situation. Ice is bad. Any questions?
What did you say the icing thing was? Boots?
Yeah, so there's a couple different things that we can do to prevent ice, and you'll get
Like the balloon thing.
Yeah, so like the leading edge of the wing, say this is like the leading edge of the wing, right? You can inflate it, and it like puffs up and will break away that ice. I've never used it, but my understanding is that you can then get rid of them and let the ice reform and then break it. It's like a balloon. The other thing, our Charlie Delta down there, Papa Delta, the green Cirrus down there has it. But if you look at the leading edge of its wings, it's like metal, like gray metal. If you look very, very closely, there's pinholes. And it actually seeps fluid, like anti-icing fluid out. It's called feety. And it's a anti-ice, not a de-ice system. So the boots are de-icing. The feety is anti-icing. And then you can obviously have heaters where most of the time they redirect exhaust air into the leading edges of the wings to keep them warmer. Sometimes it's electric. That would be anti-ice and de-ice. And then you could also have you can get de-ice, like at an airport they spray you with multiple chemicals. Has anybody's airliner ever gotten a shower like that before you took off? Yeah, so that is a anti-ice. Go ahead.
So if your wings are above the cockpit, you won't be able to see ice forming. If they're below the cockpit, you might be able to see
So-
the ice problem.
You would want to, so like the Cirruses, and you can see the leading edge of your wings from a Skyhawk if your wings are above. It's harder, you have to adjust yourself, but you can. The Cirruses have ice lights that shine directly on the wings so you can see if you've accumulated. the Cessnas, you can look at the strut right there to see if you have ice forming. A lot of times it'll form around your windshield, like you'll see other places other than your wings. But have you guys gone over the different kinds of ice yet? That'll probably be next time. There's two different kinds, clear, rime, and mixed. Clear ice is gonna be hardest to see because it's clear. Rime ice is gonna be like more chunky, airy. Ice, it's gonna be easier to see. Clear ice is just as dangerous. You might think, oh, it's nice and slick with the wing. It's not, it's still changing your angle of attack. The reason that's most dangerous, especially in airplanes with autopilot, because you might be sitting back relaxing and the autopilot's compensating and giving you more and more angle of attack to keep you from descending because you're losing lift and increasing drag and weight. And so you're going to get higher and higher angle of attack. You could just be sitting there relaxing, not watching your Netflix, and the airplane's going to stall because it has so much ice. And you didn't realize anything was happening because it's so gradual.
Yeah, the autopilot will kick off. That's what we
It
get
should.
out of tolerance, and then you'll
Yeah.
be like, "What the hell?"
Yeah.
And then you're gonna be panicking.
So don't fly in. There's no reason for small airplanes like ours to fly IFR in near freezing conditions. Make sense? All right, let's do a couple questions. Radiation fog needs which of the following to form? Delta?
Go.
Most severe weather can be found in what? Oh, this is a good one. Bravo? Who doesn't agree? Come on, be the black sheep.
Why is it?
A?
No,
Oh,
I think.
all right,
it's A too.
B. It's fine. All of the Earth's weather is due to what? Stability of the atmosphere is a measure of what? Delta? I'm a little unsure there. The suffix nimbus means what? All right. You can keep your tests, bring them next time, and bug whoever teaches next to tell you or to go over it with you.